I'm Jorji Nonaka from Riken RCCS in Kobe, Japan, and with my colleague Fumiyoshi Shoji, also from Riken RCCS, we will present a simple and practical bench testing environment for analyzing hot water cooled processors named HUD Oden. It is well known that liquid cooling has been widely adopted on modern HPC and data centers, and although there are different approaches, here we will focus on those using cold plates which are attached to the heat sources such as CPU and ICC, as shown in the K-computer example on the right side. The already decommissioned K-computer used inlet water temperature around 15 degrees Celsius to meet the operational requirements. However, for the energy efficiency reasons, the use of higher inlet water temperature in the warm and hot conditions has been receiving increasing attention. And we can cite the ASHRAE thermal guidelines for liquid-cooled data processing environments, where the Class W4 allows water supply temperature up to 45 degrees Celsius and even higher temperature for the Class W5. However, when considering the use of higher inlet water temperature, we should take into considerations not only the benefit, especially on the cooling facility side, but also the possible side effects on the HPC system side, such as performance degradation and power consumption. And it is probably easy to guess that the practical evaluation using production running HPC system is difficult and usually under limited conditions, and obviously cannot push to the limits. As an example of the practical evaluation within limited conditions, we can cite the K-computer case where the inlet water temperature of a compute rack was increased by 10 degrees Celsius, but it was still within the acceptable operational range. Another example is the use of Oak Spark supercomputer operated by the Joint Center for Advanced HPC, and the details can be found in the short paper that we presented at the cluster conference. To better understand the operational behavior and impact on the system side, we have focused on a practical evaluation environment capable of emulating supply water temperature of ASHRAE Class W4 and W5. And as an initial attempt, we focused on the component level evaluation, mainly processors, that is CPUs, GPUs, and accelerators, and also using commodity off-the-shelf equipment and components, including cold plates and dry break connectors. The most difficult part was to find a temperature-controlled liquid circulating equipment with chiller and heater. And at the time when we started this work, we could not find an equipment such as shown here, and we focused on a circulating water bus used normally for in vitro experiments. We acquired the ASWAN MCX450 with a water tank, water pump, chiller, and heater as shown in this diagram. And we connected flexible hose with dry break coupling to facilitate the changing of the evaluation targets. The temperature-controlled water flows to the cold plate, also known as water blocks, to remove the heat from the processors. And here we are considering CPUs, GPUs, and accelerators as the evaluation targets. And we named HUD Oden because of the water container format filled with warm or hot water that is similar to the Japanese hot pot dish called Oden. And when using water as the coolant, users can set the temperature from 5 to 90 degrees Celsius. And this equipment uses both chiller and heater in order to maintain the water temperature within the selected temperature set point, as we can see in this power consumption graph, using the log data obtained from the portable power logging device, showing the right side. And we can observe the intermittent use of heater, chiller, and both heater and chiller. As a test case, we utilize a liquid-cooled workstation with an Intel Xeon Phi Nightlander 7210 to analyze its operational behavior at hot water temperature condition. For the evaluations, we use the shared memory version of the Limpak from the Intel Math Kernel library, and here we will present some additional results other those shown in the short paper. We set the problem size as being 60K, which gave the highest performance from a benchmark test by changing the problem sizes. And we used some software tools for changing the frequency scaling governor and to log the CPU information such as temperature, frequency, and power consumption. For example, these graphs show the CPU temperature and frequency when using inlet temperature of 35 degrees Celsius and by using the performance and power save as the frequency scaling governors. The red line shows the base frequency, that is 1.4 GHz, and we can verify the effect of the minimum frequency during the AVX throttling on the obtained Limpak performance. And here we can observe the behavior on the power consumption, especially within the AVX region. And these graphs show the CPU frequency variation when changing the inlet water temperature from 35 to 45 degrees Celsius. And we can clearly see the impact on the frequency and as a result on the Limpak performance. And here we can also observe the influence on the power consumption. And by using this evaluation environment, it was also possible to observe the influence of the thermal throttling on the CPU frequency. And in these graphs, the thermal throttling events recorded from the Linux kernel are higher on the right side case, and we can observe the impact on the CPU frequency. And here it shows the influence on the power consumption. And it is important to mention that these results are not conclusive and only show some example of quantitative data that can be obtained by using the HUD Oden bench testing environment. And in this short paper, we presented a simple and practical evaluation environment named HUD Oden, built by using commodity off-the-shelf equipment and components, which enables component-level quantitative analysis at hot water temperature conditions of ASHRAE Class W4 and W5. We expect that it can be used to obtain quantitative data and supporting evidence for assisting strategic planning and decision makings for the HPC operations. As the future works, we expect to continue analyzing different processors, including CPUs and GPUs, and hope to have a chance to analyze also the A64FX CPU used in the Fugaku supercomputer. At the end, we would like to thank our colleagues at RIKEN RCCS listed here, and also the research group at the Federal University of Pampa for the technical discussions. And we will be happy to receive any comments or questions, and also would like to thank you for listening.